Hello physics students, and welcome to this video on momentum and impulse. And we're going to be talking about two big ideas, momentum and impulse. We'll look at linear momentum, the impulse momentum theorem, and then we'll also look at how stopping time and distance are affected by that impulse momentum theorem. In science, momentum has a very specific definition. It is mass times velocity. And you're all familiar with this concept because you know that if we have this truck and this car traveling at equal speeds in opposite directions and they collide, you know which one has greater momentum. Well, the one with greater mass. Equally, if we have a fly traveling at a particular velocity and it hits this vase, it will not have the same impact as this car traveling at that same velocity hitting this vase. That's because they have very different momentums. Equally valid is the velocity. If we vary the velocity, we definitely vary the momentum. Two objects can have the same mass, be traveling at different velocities, and definitely be having different momentum. So we have looked at Newton's laws, and we've been able to explain why motion changes when these different collisions happen. In this video, we're going to look at how the force and the duration of the collision between the objects will affect their motion. Let's go ahead and define linear momentum. We use a lowercase p, and p is equal to mass in kilograms times velocity in meters per second. That means our momentum will be measured in kilogram meters per second. And momentum is definitely a vector quantity. Its direction will be the same direction as the direction of the velocity. Now let's look at something that is called the impulse momentum theorem. Now, when Newton actually wrote his second law mathematically, he didn't write F equals ma, he wrote force equals change in momentum over change in time. This equation actually can very simply be converted back into force equals mass times acceleration. We know that change in momentum would just be mass times the change in velocity. And we know that change in velocity over change in time is simply acceleration. So we can get force equals mass times acceleration from that. We can rearrange this equation to be written in terms of force times change in time equals the change in momentum. And when we rewrite our equation like this, we call this term right here the impulse of the force for the time interval. And this helps us to think about momentum in these terms. A small force acting for a long time can produce the same momentum, the same change in momentum, as a larger force acting for a shorter time. And this is why follow-through is so important in many sports. For example, when this batter is hitting the ball will experience a greater change in momentum if that batter follows through and keeps the bat in contact with the ball for a longer period of time. So let's do some example calculations using momentum. Let's say we have a 1,400 kilogram car moving west with a velocity of 15 meters per second. What is the momentum of the car? Well, let's write our equation for momentum. We know momentum equals mass times velocity. We're given the mass, and it's already in kilograms. It's very convenient, 1,400 kilograms. And we're given the velocity at 15 meters per second going west. When we multiply those together, we get 21,000 kilograms meters per second west. And that is the momentum of the car. Now let's say the car above collides with a utility pole, and it's brought to rest in 0.30 seconds. Find the magnitude of the force exerted on the car during the collision. So first, let's write down everything we know. We know our mass, our change in time. We know the initial velocity is 15 meters per second to the west, which would be negative 15 meters per second. And our final velocity is 0. It will be stopped. And we want to find the force. We would like to use our impulse momentum theorem equation here, force times change in time equals change in momentum, which equals mass times final velocity minus mass times initial velocity. At this point, we can look at this in several ways. We already calculated part of this. The mass times the initial velocity, we calculated that up here. That was 21,000 kilogram meters per second to the west. But we can write this in several ways. We know we want to find the force. I'm going to rewrite this as force equals mass times final velocity minus mass times initial velocity over change in time. We can plug these values in from up here. With 1,400 kilograms times its final velocity of 0 meters per second, I'm going to subtract what we already know to be our 21,000 kilogram meters per second. This number will be negative because we're going west, so it will be going the opposite direction from the force that is exerted on it. And so I will make that a negative number, so this number ultimately will be positive. And my change in time is 0.30 seconds. When I punch all those numbers in, I end up with a force of 7.0 times 10 to the 4th newtons to the east, or in the opposite direction of the velocity of the car. Now let's look at the idea of stopping times and stopping distances. They both depend on the impulse momentum theorem, and you know this intuitively. You know that this truck must undergo a greater change in momentum in order to stop than this car. So let's look at an example with stopping times and distances. A 2,250 kilogram car traveling to the west slows down uniformly from 20.0 meters per second to 5.00 meters per second. How long does it take the car to decelerate if the force on the car is 8,450 newtons to the east? And how far does the car travel during this actual negative acceleration? Let's start by writing down what we know. I know my mass is 2,250 kilograms. I know my initial velocity is 20.0 meters to the west. So I'm going to designate that negative because it will be to the west. So I'm going to say 20.0 meters per second. I know my final velocity is going to be 5.00 meters per second to the west. So I will also designate that as negative 5.00 meters per second. I know that the force that is exerted on the car is 8,450 newtons to the east. So I'll designate that in the positive direction because it's to the east. So 8,450 newtons. My change in time is unknown and my change in distance is unknown, and I would like to find both of those because it asks how long does it take the car to decelerate if the force is 8,450 newtons, and then how far does it travel during that negative acceleration. So first I will find my change in time by using the impulse momentum theorem. I'm going to rearrange this theorem to suit my purposes a little bit better in terms of delta t. Now I can just plug values into my equation and solve. And I apologize, I kind of ran out of room there for the rest of those terms, but I'm going to divide this then by the force, 8,450 kilogram meters squared per second squared. And when I punch that into my calculator, I get my change in time of 4.00 seconds. So that's how long it takes for that car to decelerate if the force on the car is 8,450 newtons to the east. Now we'd like to find, so we found our change in time, we'd like to find our change in x. How far does the car travel during that negative acceleration? I'm going to use one of my kinematic equations. Delta x equals 1/2 times the sum of the velocities times the change in time. Now I can just plug my values in and solve for the distance. There I plug the values in, and when I multiply that out on my calculator, I get negative 50.0 meters, and that would be the same as 50 meters to the west. Remember, I had set my coordinates as indicating that negative would mean to the west. So I'll say this is 50.0 meters to the west is the amount of distance that that car traveled. So one last parting thought is that the impulse momentum theorem allows us to realize something, that the change in momentum over a longer time will require less force. So I'm going to rewrite that theorem right here for us so that we can keep that mathematical representation in our minds. In both of these situations, we have the force of collision being reduced by allowing it to take place over a longer time interval. If this man hits this pad, there is a longer time interval that happens because of that pad. So the force of that collision is reduced. If the man were to hit simply the ground, he would not have the benefit of that long time interval, and therefore the force of that collision would be much greater. Same with this egg, and you know that because if you were to drop an egg and you were to have it hit the tile floor in our classroom, there would be a much different result. And the result would be different because the force of impact would be much greater because the time interval that that force was occurring over would be short when it hits the tile, whereas this pillow allows a longer time interval, and therefore the force of the collision is reduced. Advanced ideas. Why do we use a P to represent momentum? Here's some other ideas for you to look up. Any other questions you have, please ask them. Look into things on your own. I'd love to see your work, and I look forward to seeing you in class.